Okay, I'm going to introduce Olivier, even if many of you already yes, know him. Olivier is a friend of many of us because after his PhD that he had in Marseille avec Laurent Stress, he stayed here in Bologna with us in 2005 and, as a first postdoc. Yeah, a few years ago. And so working on galaxy surveys, especially at the time for the BBDS with Elena, Gianni, Lucia, and the others that were involved at the time in the Venus VLT deep survey. And then after the first PhD, he moved in Hawaii for postdoc working on Cosmos and Spitzer data. Then he went back to Marseille, where he's a full professor since last year. And well, his work, many of you already know it. He's the author of Le Phare, the Proto-Z code that many of us are using. And he's developing algorithms for the stellar mass functions and luminosity functions and to derive physical properties of galaxies. And he's undoubtedly one of the pillars of the Cosmos survey, besides many other that we had with the Venus instrument, but especially in Cosmos, his contribution is fundamental. And he's going to present us some new results on the Cosmos web with the explicit data of JWST. So thanks.
Thank you, Nicole. And that's great to be in Bologna again. That's a great institute, and I'm really happy of the week we spent here. So I'm going to present the works that we are doing right now on Cosmos, mainly with the James Webb data. And first, I'm going to do an introduction, if it is working. Okay. Okay. So I need to say that in the last 2 years, it has been really amazing. Since this Christmas of 2021, where we got this James Webb launch, like the amount of data that we got on galaxy evolution is really incredible. And first, I think like I've been stunned by the beauty of the data that we got with James Webb data. And here you can see two local galaxies by Fang, and all the details that you can get on the galaxy is really amazing. So that's also a great tool for the iterative universe, and I guess most of you saw this first image by James Webb with this cluster, where you can see all the details with the arcs and all the lensing that we can derive from this cluster. So that's a great tool for the iterative universe, and you will see that in this talk. That's not only the images, which are great. I've been really amazed by the quality of the spectra. I'm not using a lot of spectra in my work, but still, that's really amazing. Like this kind of spectra at redshift 6.3, so that's from JADE, where you can see all the emission line 03 H alpha. You could believe that it is something take on local galaxies. So that's really amazing, the capacity of this instrument. So, but more than James Webb, we are really lucky. We have two great telescopes. We have Euclid, which has been launched 1st of July in 2023. And also here, the data are really amazing. So I guess most of you saw the images from these. So the great advantage is that you have this field of view of 0.3 square degree. And you can see all the quality of the image similar to the Hubble. And so that's going to be something great to study galaxies. And the great news is that the survey started. It started last week, so that's a great moment. And we will have billions of galaxies. We should have millions of spectra also. And so we should cover an area of 15,000 square degrees. So that's going to be a huge tool to study galaxy evolution. So more than the beauty of the data, what we want to understand is really the physics driving the galaxy evolution. And so I'm going to do a short introduction on that. So now we have great simulation, hydro simulations that you can trust, many of them. And what I want to say here is that there is an extreme complexity in all the processes in this simulation. And first, because you have a lot of physical processes included in this simulation, these processes act from the parsec to the megaparsec scale, so on a large range of scale. Some of these processes are interconnected. That's also make it difficult to study. And also their relative importance will depend on the age of the universe that you will consider. So that's why it's so difficult to study galaxy evolution. And I think it is too sure, like the James Webb, Euclid, but also the future survey like LSST, Roman, or SK, they will be great to understand galaxy evolution. I think we can set a lot of these mechanisms in the next decade. So to understand galaxy evolution, you need to have the cosmological context. So why is that? Is that because you have your large-scale structure. So here you have the illustrative simulation. This is dark matter. This is the gas. And so you can see that with time, you have the large-scale structure, which are growing with time, and the halo, which are becoming more and more massive. And the important point for galaxy evolution is that the gas is following the evolution of the large-scale structure. So it means that since you need the gas to form your galaxy, to form the stars, it means that it is really at which rate the stellar mass structure will grow, the dark matter structure will grow, which will set the star formation, the rate of star formation. So that's really important to understand how this dark matter structure grow. And hopefully that's something which will happen in the next few years. So we have already a lot of CMB experiment with, for example, Planck. And today, like we have this concordance model, which is the lambda CDM. But the goal of this future mission, like Euclid, LSST, Roman, but also DAISY, or a lot of different surveys, is really to understand this growth of the dark matter structures. So this is something which will really be constrained in the next 3 years. Then you have your large matter, dark matter structures with the gas which are growing, and then you need to have the gas falling on your halo. And this is quite important to see. That's really a complex process. So for instance, here you have this simulation by Deckel, 2009, where you can see here the radius, and you can see the virial radius, and you can see that you have some filaments going directly through the virial radius, and this is happening mainly at really high redshift. At low redshift, you will have the gas which will be heated at the virial temperature. And so what does it mean is that if you take here the halo mass and the redshift, when you have a mass below 10 to the 12 for the halo mass, you can feed your halo with cold gas. But if you are above 10 to the 12, basically at low redshift, the gas will be hot and you cannot form a lot of stars. You stop star formation. At high redshift, you have this cold stream, and you will be able to form gas, to form stars much more easily. And this has a strong impact on the formation of massive galaxy at high redshift. So also something is that it's clear now from a lot of measurement that at high redshift, the fraction of molecular gas inside the galaxy is much more important than that what you have at low redshift. And this has really a lot of impact on the star formation, but also on instabilities that could develop inside the disk. So now that you have your gas, which is falling from the halo to the inside the halo to the galaxy, you can do some star formation. That's working. So the important point is to realize that the star formation is really inefficient, and the reason for that is stellar and supernovae feedback. So basically, what is happening is that your gas is converted into stars. The stars, the massive stars, you will have some wind, and you will have supernovae, and all this energy will stop the star formation. So that's the kind of regulation that you will have inside the galaxy. And I like this figure from that's a simulation by Torre in 2014. That's a hydro simulation. And so that's what you can see is the mass function. I will use that a lot after. That's the density of galaxy as a function of stellar mass. The data point are the black point here. And you can see the simulation without any stellar feedback is the gray line. And so you can see that stellar feedback is really what is regulating the growth of most of the galaxy. And you can see here they have a lot of different ways to implement the feedback. And depending on the ways they implement the feedback, they will completely change their prediction in the mass function. So it means that the galaxy stellar mass function is crucial to constrain the processes of the stellar feedback. And that's something we try to bring with the observation. Last point I want to make is also extreme events will play a crucial role in galaxy evolution. Obviously, you have the merger between two galaxies. You will grow the stellar mass much faster with this process. But also, this merger could trigger a burst of star formation. So you see here the star formation rate as a function of the time relative to the merger. That's a simulation by Hopkins. And you see that at the time of the merger, you have a burst of star formation. And then you have an AGN, which is starting inside the galaxy, which is like a bright mode AGN. And it stops the star formation. It's what we call quenching. And this will stop the star formation in the most massive galaxy. So this is probably something crucial to understand galaxy evolution and the formation of massive galaxies. So in this talk, I will concentrate on one aspect of the stellar mass, the evolution of galaxy, which is the stellar mass assembly. So I will present some results on the first massive galaxies that we find above redshift 10. That's strange to say that, but above redshift 10. I will show some results to understand how the galaxy grew with time. So we have this famous Lily-Madao plot. A lot of you here contributed to this plot. So that's the average evolution of the galaxy with time. And also we'll present some results which allow to link this star formation, the stellar mass assembly, with the mass of the tail. So everything that I'm going to show, all the results I'm going to show are done on the cosmos field. So as Nicole said, I work a lot on this field since 15 years, even more. So that's a field of 2 square degrees. So we have more than 1 million of sources in this field, depending on the selection. The advantage of this field is that we can limit the cosmic variance, even if now we will have a huge survey coming, but that's for this sensitivity, that's one of the biggest fields. And you can also study large-scale structures, so that's a big advantage. So behind you can see the ultra-vista image, which has been produced by Henry McCracken, that a lot of you know. So what is really unique, I think, also with this survey is that we have a coverage, a multipolar coverage, which is really deep, but also with more than 30 bands from the UV to the near-infrared. So that's great to get the photosy. We have a coverage going from X-ray to radio, which is great if you want to study AGN, for instance, or a lot of different things. And also, this survey is in constant evolution since 50 years. We always have new data coming. So this survey is completely changing with time. And also, it is sufficiently deep for this area to reach a galaxy above redshift 7. So that's a good combination of sensitivity and size of the field. So I'm going to show a few slides, a few results now, which that I put James Webb. So that's the result that we got 2 or 3 years ago. And after I will show the results with James Webb. So this is, first I want to introduce the Cosmos 2020 catalog. So that's a catalog that we did with John Weaver, mainly, and Olivier Kaufmann. So that's a catalog where we have more than 1 million of sources. We get photosy and stellar masses with Easy and Lefar for the full catalog. And we release completely the catalog, so a lot of people are using it right now. And so you have here the photosy versus spec-Z. So that's one for one of the flavor of our catalog. This different bin in apparent magnitude in high band. So for instance, for the bright sample, you can see that we have an accuracy better than 1% in the photosy with less than 1% of catastrophic failure. And it degrades when you go to fainter magnitude. For instance, in the faintest bin above 25, we don't have a lot of spec-Z, but oh yeah, it's quite consequent. So we have like a precision of 4%. So we have the masses, and with that, we derive the galaxy stellar mass function. So this is the result from John, where you have the density of galaxy as a function of stellar mass. Each color corresponds to redshift bin. So here, even without James Webb, we were able to go up to redshift 7 here. So not with a lot of galaxy and with large error bar, but we were able to go there. And you can see the galaxy growing with time, increasing in density. So that's great measurement for great constraint for simulation. Also the shape, the slope of the mass function. You can integrate this galaxy stellar mass function to get the stellar mass density. So galaxy stellar mass density as a function of redshift. And you can see that the galaxies are continuously growing with time, hopefully. And so you can measure the fraction of galaxy, of stellar mass, which was already assembled at a given period. So now I'm going to enter in more detail and try to see what we can say on the physics with this galaxy stellar mass function. So that's exactly the same galaxy stellar mass function as shown before. So here you have the stellar mass. So we started here at 1.52. So you have the galaxy stellar mass function in different redshift being from 1.5 to redshift 6. And the interesting point in this figure is that we have here, in this part, we have the dark matter halo mass function multiplied by the universal baryonic fraction. So basically that's if you convert all the baryons that you have in your halo into stars, you will get this galaxy stellar mass function. So basically, if you have a mass function which is going above this limit, it means that you are converting all the baryons from your halo into stars. And you will see after that's quite important for all the results that we will discuss with the James Webb. A lot of people discuss that right now. So, and here that's just with a factor, like if you take 10% of them. So the first thing that we can notice on this figure, so that's what I just explained, sorry. I forgot that I put that. So what we can notice here is that first we have a really inefficient conversion of baryon into stars. And we will use a lot this, so people call that sometimes star formation efficiency, but that could be mixed with other definitions. So we use effective stellar baryon fraction. I don't know if it is better, but basically that's the ratio between the stellar mass and the mass of the halo multiplied by the universal baryonic fraction. So that's the fraction of gas that you convert, of baryons that you convert into stars. So you can see here that that's not really efficient, even in for the halo mass, which is the best for that. And if you look now on the extremity at low mass and high mass, you see that the shape, you have this Cheshire function shape, where you have this exponential cutoff here at high mass, and also the slope is not as steep as the one of the dark matter halo mass function. And the reason for that is all the feedbacks. So that's what I explained in the introduction. Here we think that it is the supernovae and stellar feedback which create this change in the slope. And also at the high mass end, we think that AGN prevent for the formation of the most massive galaxy. So from this plot, what you can see already is that at redshift 1.52, you have already the supernovae feedback and AGN feedback, which are in action because we stop the star formation in the most massive area. So let's move now to our redshift, and that was the result from John, and we spent a lot of time on that. That on the high mass end, you can see that we have much more galaxy than what we were expecting from the simple model. And we were finding more galaxy, even at some point, galaxy close to the limit where we should use all the baryons. And we were quite skeptical about that, but we did a lot of tests in the catalog, and that was remaining. So that's something that we found, and we discussed a lot in the paper. And you will see after with James Webb, that's exactly what is happening today. So we work a lot on this part. And so basically, it means that something is different in the redshift universe. And the question is, maybe the AGN feedback is not efficient yet on this high mass regime. Maybe the code accretion is so efficient that you can convert much more easily your gas into stars. You can have instabilities in the disk, which makes them more efficient to form stars, or observational bias, and that's our main worry, that's our work, is try to understand what is going wrong with this, or not, with this really massive galaxy. Because here, everything is done with photosynthesis.
Excuse me, it's a bit odd that this doesn't happen in this.
Yes, yeah, I agree. So you will see after basically we have a new research with James Webb, and that's what we are studying right now. So that's the point we were basically that's we spend a lot of time trying to understand that these galaxies are really red, and the point is that they are so red that it's difficult to measure photosynthesis for them. Even if they are the most massive, they are bright, but given the amount of dust, that's really difficult to constrain their photosynthesis and their properties.
Olivier,
Yeah.
how solid is the FB, the 0.018 number? Because I mean, is the one that help you to those limits.
So
Well, I remember a slightly different number about the universal baryon fraction. So
okay.
I wanted to know.
Yeah, so TISA, I think they use the latest Planck result. For
what? Sorry.
Planck results. Yeah. And this value here that they use for the this solid line here, it's something coming from I think Beruzzi. Yes.
There are also some results from simulation that the fraction of baryon could depend on the halo mass.
That could be one explanation. This could be another
be-
explanation. It was discussed too. Yeah, I totally agree. But so if you assume this value of Planck, that's the limit that we have here. You will see that after people put also the mass of the halo directly. So like this, if you are above the mass of the halo, you are really in trouble at this point.
Sorry, you were adding to. I can ask you this later.
That's fine. I don't know what you are doing usually.
So I respect that the number of these massive galaxies will at least grow or stay stable, approaching redshift 0. Instead, it looks that these massive galaxies start decreasing in number densities.
So can I come back or not? Let me see. Okay, so here you have all the mass function together. So you can see that at my side, you are still growing in mass. So that's not inconsistent. There is no problem of consistency here. But you can see that at some point you arrive at this limit and you stop completely to grow the most massive galaxy. So this is expected. Basically, you have the agent feedback, you stop to grow them, and you cannot form new. So you have just a merger to form them. So maybe I will go on and show you the James Webb result like this. We can discuss with more reliable data.
Olivier,
Yeah.
and cosmic variance may play a role.
That's included in the error bar. For me, I think the most problematic. So cosmic variance could be a problem in the local measurement. 0.2, 0.5, you could have like real variation on the high mass end. Here, I don't think that's the problem. I think the problem is the quality of the photosynthesis that you need to derive. Okay, let's move because I think I would be really late. Okay, so the last point I wanted to present this paper by Marco Shantov that you saw last week with postdoc now in Down, and he was a PhD student at IIP when he did that with Henry McCracken and Raphael Gavazzi. That's again on the Cosmos 2020. So just I don't enter in detail. He computed the clustering, the angular clustering in different redshift bin with this Cosmos 2020 catalog and the mass function, and he's using that to constrain the relation between the stellar mass and the dark matter halo mass. So I don't enter in detail for this measurement. So what he's doing is using a HOD model. So basically that's a model which link the mass of the central with the mass of the halo and the number of satellites as a function of the mass of the halo. So you have 11 free parameters. So I will not be able to describe again. I don't remember very well the meaning of all these parameters, but you have basically the slope of the number of satellites and this kind of stuff. And so basically you populate your dark matter halo with galaxies and you fit this parameter. And that's a really nice paper in which he derived at the end one of the main results is the stellar to halo mass relation. So that's the same kind of paper which was done by Alexis Otto, for instance, where you have the ratio between the stellar mass and the halo mass as a function of the halo mass. And you can see this shape here with the peak around 10 to the 12. So again, it's telling you that it is in this kind of halo that the star formation has been the most efficient. And you can see here again, probably the effect of supernovae feedback and AGN feedback. Something that he found also, but you see the large error bars, is that the position of this peak is moving toward the high mass halo when you are going at higher range. But anyway, I think that's a really great tool to compare the stellar mass and the halo mass. So this relation is a great tool when you want to link the two. And I will show you after that we use that in James Webb. Okay, so let's move to the new data. So basically, we got this proposal accepted Cosmos Web like 2 years ago. So that's mainly imaging, where you have NIRCam images and MIRI images. You can already find this overview paper by Kathleen Casey and Gian Carter-Tepe, who are the PI of Cosmos. You can see here the SES coverage of Cosmos, and now the coverage in NIRCam, which is the blue area, and the coverage in MIRI, which are the red pointing. Yeah. So we have at the end 0.54 square degree for NIRCam, 0.2 square degree for MIRI. So this survey was designed to catch the most massive galaxy at the epoch of ionization. So you can see that that's a figure from the proposal, I think, where you have the Lyman break galaxy at different redshift. So we took the most massive one. Here you have the limit of NIRCam, and you can see that you can detect this massive Lyman break up to redshift, we hope 13. Here you have the passive galaxy, and the idea also is to be able to get a passive galaxy, the first galaxy which quenched because of AGN feedback, up to redshift 4 or more. So that was the two main goals, and there is a goal which was to link dark matter with visible light using lensing. So this I didn't follow well for the moment what they are doing. So that's the third part of the survey. So this is the sensitivity we want to reach. So we have the 4 NIRCam band, one at 1.1, 1.5, 2.7, 4.5 micron, and the MIRI band at 7.7 micron. And in NIRCam, we have sensitivity between 27.5 and 28. So basically, thanks to that, we can reach the really errative universe. So this is the first images we got in January 23. So you can see that this data from January. This is the mosaic created by Maximilien Franco in Austin, and this is some zoom on some really nice galaxy we have on the mosaic. So this mosaic is already was released 6 months ago, so you can already use the mosaic as they are available. So now the good news is we got the full survey, which is great news. So we got that 1 month ago. So we have almost all the pointing which are observed. We are still missing few. There was some failure here, and this will be reobserved in April. But basically, we have now our full coverage with NIRCam and MIRI. I can show you the mosaic. So that's again the mosaic done by Maximilien Franco. So he created this mosaic 1 or 2 weeks ago, I think. So you see the missing part, but here you have the full area. So I can zoom on some region, for instance, here. So you can zoom on this region, which is a small region of the field, 8 square minutes, and you can see the density of sources that you have and the quality of the morphology we can get from this kind of survey. So I zoom on another part. For instance, here, that's another part. You can see some structures here, and so that's a great data. So just what I realized this morning, I didn't realize it. So this part was observed in April, and everything is public. The mosaic is already released. I think it was released last week. I didn't follow that well. So this part is already public, if you need. Okay, so we are working on the mosaic right now, trying to improve the quality. This is some selected object that Wilfried Mercier at LAM selected. So we look at different tiles and keep the objects which are looking really nice. So for the moment, we didn't analyze them, but I just show them for fun. You can see arc, you can see dwarf galaxy, you can see probably merger. This we still don't know exactly. So basically, you have really nice collection of objects. So, and Wilfried, with the first epoch data, found this extremely nice Einstein ring. So I'm going to spend a few slides on this ring because I think that's really nice. So I don't know if you saw, there was another paper on the same Einstein ring by Don Dokum. Like basically published, put the paper on AstroPH 2 weeks before us, so too bad for us, but still, I think this object is really great. So basically, you have the Einstein ring here, you have the elliptical galaxy, and what you can notice here is that you don't have the same shape of the Einstein ring in the red NIRCam band and in the blue NIRCam band. You can see 2 red clumps here, and here you can see more diffuse light on this side of the Einstein ring. So what we did is that we modelized this ring. So I'm really not an expert in lensing, but so that's something that has been done by Raphael Gavazzi and James Nightingale. So they modeled this lens. So that's the images, that's the model by Raphael, and that's the residual. And so like this, we can derive information on this lens that I'm going to show you.
So the modeling has been done at different wavelengths?
In the case of James, he did that for 4 different wavelengths. And one wavelength is, so 3 of the bonds are really consistent, and 1 bond is not so consistent. And also, Raphael used the 4 bonds at the same time. You will see that's how we derive the photometry. Okay, so we derive the photo-Z for this system. And here you have the lens, which is in red. So that's the photo-Z I got with LeFar, but we try also Seagal and Easy, so other codes. And so the point which is exceptional with this object, which is an elliptical galaxy, is that the galaxy is probably at redshift 2. So our photo-Z gives a solution at redshift 2. So that's probably the highest lens that we know in this field, well, in general. So the second point is the redshift of the source, and this is quite important because basically we don't find the same redshift at all as Peter van der Boom, and this changes completely the conclusion of the 2 papers, so which makes them interesting. So we don't have at all the same redshift, so we find something at redshift 5 here. So with the 3 different codes, and so the point now is try to understand to secure this redshift. So here, that's closed by sources which contaminate the photometry. But you will see, we try to secure this redshift. And so this is a tentative spectroscopic redshift we maybe managed to get, but that's still tentative. So we got that with Mossfire. So that's Rebecca Larson who took the data. And you can see here, there is, for them, that's a clear emission line in O2. Looking in detail to the data, I think that's really clear. The emission line is clear. And when you look at the spectra, you see the O2 line here. So that's here we rub in the data. So we saw only 1 line in the spectra. And basically, the point is that if it is the O2 line, as we expect, it's redshift 5.1. So we don't see any other line. So if it is redshift 3, we should see the other O3. We don't see it. So and we are like the width of the line is consistent with the doublet. So using some tool to measure the spectroscopic redshift, we got the best solution is the only solution is as 5.1. But still, we are trying to get more telescope time, better sensitivity to get the doublet and to say more about this galaxy. But for the moment, that's inconsistent with our solution at IZ. So now let's use a bit. Let's do a bit of science with this object. So basically, what you are doing is you model this source. And with the different model of Raphael Gavazzi and James Nightingale, we can get the total stellar mass, which is inside the Einstein ring. So we derive a mass, which is here at 3 and 10 to the 11, consistent with the 2 code. And what is really interesting is that we can subtract inside this Einstein ring the total mass minus the stellar mass of your object. And so that's what we call the remaining mass. And the question is, if this remaining mass is completely dark matter, is it consistent with the stellar 2 mass relation that I showed you by Marco Shantov before? And so that's what I show here. So that's a bit complicated as a plot, but basically for the stellar mass of our object, we can get, using the relation of Marco, we can get the expected mass of the dark matter halo. And this is the expected mass of the dark matter halo. And then you can extrapolate and understand like the expected dark matter inside Einstein radius, which is this value. And this value needs to be compared with the remaining mass that we compute that just in the slide before. So basically, what you can see is that the mass that we expect from the stellar 2 mass relation is very well consistent with the one we get from the measurement.
So how did you extrapolate from the mass in the Einstein ring?
With the Navarro-Broken-White profile. Yeah. So at least what we can say is that with our current measurement and with simple modelizations that we have, at least we have something which is consistent with what is obtained with the stellar mass function and the clustering. The point here is that basically, if you take another redshift, a redshift 3, you will find that nothing is working and that you need to change completely the dynamics. Okay, so that's why the two conclusions of the two papers are so different. And that's mainly because of the redshift of the source behind. So the redshift of the lens, we need also a spec Z, would be great. We have a good constraint on the photo Z, but as long as we don't have a spec Z, that will always a doubt. Okay, so last point that I can make on this lens is that we were able, using the two software, to reconstruct the shape, the morphology of the source behind. And basically, the reason for which the Einstein ring is different in the blue and red the bonds is that probably we have an extended emission here, which is really blue, and here a clumpy, something compact, really red. And this may be explaining why the Einstein ring depend on the wavelengths. So of course we try, like the idea is try now to do more with this lens and try to have ALMA time to say more about this source behind, because we can reach a really good spatial resolution of the source. Okay, so that's it for the lens, and now I still have time. Okay, so let's try to do some statistic with the catalog. So we have a Cosmos Web catalog. So basically, all I'm going to show here is done with the data from April, so half of the field, because we got the data 2-3 weeks ago. We are doing the catalog. I was hoping to show you that, but it failed yesterday, so I was not able to show you the latest result. But that's done on half of the data. So we use source extractor ++, which is a code developed by people by EAP and Geneva to derive the photometry. So you have the NIRCam data, and you want to combine with the ground-based data, which are here. And that's you can see the difficulty because resolution is totally not the same and sensitivity is not the same. So that's why such tool is important. And so that's the work done by Marco Shuntoff and Luis Pacoro in AAP with Henry. So you have the image, NIRCam image segmentation. You combine all the galaxies which are close by, and you will see that we do the photometry of all these galaxies in the group together. So to do the photometry, we do this profile fitting. So we have a surface brightness profile. So we use either CERSIC or bulge plus disk model, and we fit this model to the observation, and we fit them together. So in principle, that's much better to handle blending. So that's the idea. That's to my opinion, that's the only way to use this ground-based data and high resolution data together. And so that's an example done by Marco, where you have the image, you have the model, and then you have the residual. So this is done with CERSIC. And so probably you see for the bright galaxy, you see the fact that we don't have the bulge. And you also run it with bulge and disk, but I don't have the example here. And here, for instance, I can show you also one result by Thibaut Moutard, with doing that for the GTO MIRI, and using also source extractor ++, the image, the model, and the residual. So that's the code now we start to use routinely to get the photometry. And of course, I don't show you that here, but we compare a lot with Aperture, Farmer, and all the different catalogs that we have. So let's move to the PhotoZ. So when we have this catalog, so in total, we have 600,000 galaxies in the catalog now. And so we run LeFar on this catalog. So LeFar is a template fitting code to a PhotoZ and physical parameter. I don't want to say a lot, just to say that we work a lot in the last few years to have the code in C++, also with Johan Cohen-Tanucci, and also to have a Python interface with the notebook. So we are still improving the code. There is the link for the release, but like we work every day on this code, so hopefully it will be stable soon. So that's what I use in all the survey. So some example of best fit template. So to be honest, like when I run that on the first generation data, I was really impressed. That's something that we are not used to see. Like the quality of the constraint in near infrared is really incredible. And you can see here one example of a galaxy at redshift 0.8. And here you see the NIRCam point. So I took few examples. So that's a galaxy at redshift 2. So here you have two possible solutions, but you can see the constraint here is really important. So red is the galaxy, yellow is the AGN, and blue is stars. This one I like it. For instance, you have the Balmer break, and you see it very clearly. That's for galaxy at radius 3. So that's now you start to have really photos which are extremely well constrained. So I didn't took randomly. I took nice example, but you have like thousands of them. I didn't took stuff with a lot of noise, but you can have a constraint which is really amazing at IZ. Last one I took it yesterday, so I didn't check the object in detail. That's redshift 7. You can see Lyman break and the shape. So I took it randomly for this kind of object. That would be much better to check on the image and be sure for what we are doing. But just to show you the kind of constraint we have. So I just put a few estimate of the accuracy and failure rate. So now we do it in apparent magnitude bin at 1.5 micron. So that's different from what I was showing before. And we have an accuracy which is 2%, 24, 25, 3%, 25, 26 at 1.5 micron. So that's really deep in the infrared. Here I have only 50 galaxies, and that's a really specific population. So I will not trust that they were selected with narrow band, so that's specific. So I will not trust this quantity. So I don't know if you saw, probably you saw this paper by Kathleen Casey, where she used this catalog to select massive galaxy at really high redshift. And that's kind of crazy, but that's above redshift 9. So that's still impressive for me. So you have these sources which are detected in NIRCam, so mainly at 2.7, 4.4. This kind of detection at 1.5, and then no detection in 1.1 and ACS. And so she selected 15 candidates in the half of the data, so on 0.3 square degree. 15 candidates, which were the brightest candidates. And here you have some examples. So we run different tools, easy, the far backpipe, to be sure that everything is consistent. We try several different photometry. So we try to do it in a clean way. We check all the images. So we rejected a lot of candidates. So I just put like few examples. Maybe this one is interesting. To everything that she has above redshift, that we have above redshift, around redshift 13, we have it only in 2 bands. So basically, we need to take that with a lot of care, because the PDF is like you can see that the PDF are much more broad. So now what do we derive with that? So this is the MUV as a function of redshift. These are the candidates selected by Kathleen, and of course we are trying to get SpecZ for them. You can see the most impressive one are this one for one redshift 12 with the magnitude of -22. So if you put them in a luminosity function plot, so density of galaxy as a function of MUV, you see the point here from Kathleen, and you see that it's quite consistent with everything which was fine with James Webb in the last 2 years. So basically, it seems to confirm that we have much more really bright galaxy at such redshift. So she did this nice plot where she took these 3 galaxies and tried with the star formation history that they derived from backpipe. 5 minutes, that's fine. So with this 3 galaxies, she derived the star formation history and found basically that you need like a star formation history which are really like a burst in the 50 last million years. So that's what she found here, and that's consistent with the sources that we find at higher redshift, which are really tentative, I would say. So something that you can see also in this plot is the stellar mass limit. With the lambda CDM, you expect one source like this, so we are really close. So yes, that's if you use all the gas which is inside the halo. So these parameters that I show you at the beginning, which is around 1, use all the baryons which are in the halo to be converted into stars. So we are really close to this limit. So the point is that so 3 galaxies like this is already a bit worrying. So, but they need to be confirmed with SpecZ for sure. So there are a lot of papers that probably you saw a lot of talk on that, or a lot of presentation trying to explain why we have such a massive and bright galaxy at IZ. You have this feedback-free model. So basically you need to use all the variants. So you need to stop the feedback. So basically that was done in this paper by Dekel. This dust-free, so that's more to say that you have no dust at high redshifts by Ferrara. You can change the IMF. You can see if there are more AGNs that we were seeking, which contribute to the light, and you can change the cosmology. So that's the last one that you can. So that's all the different papers which appear by all the theoreticians that you can see on AstroPH in the last year. Okay, so let's move now to the mass function. So that's the same plot I showed at the beginning with the direct data in the paper of John Weaver. And now we try to do exactly the same with Cosmos Web. So that's this plot was done last week. So that's really preliminary. So take it with a lot of care. So we are working a lot on that and trying to have, we will try to have it on the full field and be sure about everything we are doing at IMAS. So basically that's very consistent with the result of John. So here you have the stellar mass function at redshift 3.5, 4.5. And here you have the one, so Marco pushed that up to redshift 8. So let's see. So here with the gray area, that's the if you use all the gas in the halo, so efficiency of 1, and then for different efficiency, 0.1, 0.2, 0.4, so with different, that's a different gray area. And so you can see again that now in the massive end, you start to enter in this region where the efficiency to convert the baryons into stars is more than what we have in the local universe. And you can see it here. So now just there is an important point. You see T square here, for instance, which are really in a region where you don't want them. So T square is if you take all the source, but you remove the stars. Then there is the problem of the AGN. So in the code, we can select AGN, even QSO, based on the point like and the basic template of the AGN. And if we do that, basically you go from this mass function to this one. So that's something we are really working on right now. The question is, do we have a lot of AGN which are maybe not at the right redshift, which are contaminated our mass function? My opinion is that that's the case. But there is probably something in the middle. So that's what we are digging right now for the paper of Marco. So anyway, I think that's up to redshift 6. I think that's quite stable, and that's really consistent with what we found with John. So, but now with PhotoZ, which I show you the quality of the PhotoZ, I think that we can trust that much more than what we got before. Okay, so I still have a few minutes, so maybe I can I want to say that I wanted to show that at the beginning during the seminar, but I'm not ready, and we are not ready with these results. So just to tell you what we are doing, we study the star formation history with the data. So we hope to be able to construct star formation history with the photometry. That's a bit, but we are working a lot with that with Rafael Arango and trying to understand the evolution of the main sequence using this star formation history. So I don't have the time to explain, but we are looking at the mass assembly splitting per type. So that's the mass function again for the passive galaxies. So that's a work by Marco again. And you can see that this mass function for passive with this, oh, I didn't put the redshift range. Ah, yes, here, 0.5, 0.8, 1.52. And you can see this nice shape of the passive galaxy. For me, that's really impressive. So that confirms everything we were saying like with pen paper and this kind of stuff. So that's really nice to see this nice power law. Even up to a redshift, you can see with the result of John Weaver that it's fit really nicely the result. So basically, last week at the conference, I think someone showed the red fraction and the difficulty to measure that. I think that's more and more stable now. And the last point is that I cannot gonna describe at all, but Luis Paco right now is working to measure the clustering on this data up to really small scale, up to really high redshift, and she's doing that obviously with Henry McCracken. So that's something we want to do. And so we got this funding by French government, ANR Image, and we have this nice group of people working on this data, and that's almost all the results I show here that was done by this Wilfried, Marco, a lot of these people in this ANR. So that's going to have this group. For the conclusion, I would say that, okay, the Cosmos Web data are fully observed now. We have half of the data which are released. So we have 4 bands going up to in the near infrared about 0.5 square degree, a huge photometric catalog with 600,000 galaxies. That's a unique way, I think, to explore the galaxy in the redshift universe. We have these 15 bright candidates at redshift 10 that we want to confirm. We work on this stellar mass function. I think that's something really interesting that we can do with this data, and we are working on like the next month is going to be dedicated to that. And so I think we are going in this direction to say that we need, for the massive galaxy at least, higher efficiency than what we have in the local universe. I think a lot of people find that now, and it seems that we go in the same direction. That's also a powerful survey to isolate rare source at high redshift, like the Einstein rings that we found. But basically, looking at the image, you have a lot of sources like this, really interesting that needs to be studied. So there is much more to come in the next year. And maybe I put a last slide to just wish good luck, because I was that picture of 20 years ago, and I went to 2 towers, and that's really scary now. So I wish good luck to the tower. That's what I'm going to do.